Hey everyone, so we already know that negative and positive attract to each other to form bonds, interactions, things like that. In this video, we're going to come up with new ways of thinking about and describing this. The new terms we're going to use for positive and negative is going to be acids and bases. Most of the time when we talk about acids and bases, we're not really thinking about charge, but you're going to see a pattern in how we think about acids and bases. Acids are going to be things that lack electrons. They could be neutral, but often they're going to be positive as a result of lacking electrons. And then bases, they're going to have a lot of electrons. They could be neutral, but usually they're going to be negative. And if you have negative here, positive here, if you have a lot of electrons here, if you don't have a lot of electrons here, this is going to be your flow of electrons. The negative and the positive thing, they're going to attract, and then electrons on the base will be used to form a bond with whatever is lacking in electrons, your acid. All right, so here's our acid-base vocabulary. We have three different categories of acids and bases. We have Arrhenius acid, Arrhenius base, Bronsted acid, Bronsted base, Lewis acid, Lewis base. All right, this is the order that acids and bases, in my experience, are usually taught in from top on down. And the Lewis acid isn't always talked about in like an intro chem 101 sort of context. Maybe not even in a Chem 111 first semester college chemistry. But I like to teach it, and this is the order that's taught. But I think for teaching it, we're going to think about it in reverse, going from bottom to top. All right, so let's start with Lewis acids versus Lewis bases. This is basically what we were talking about earlier. Lacking electrons versus having an excess of electrons. All right, if you have a lot of electrons, you'll be considered an electron pair donor, and those electrons will go to the Lewis acid, which will accept those electrons. All right, so that's the difference between base and acid. The Lewis base will have a lone pair source. It'll be a lone pair source. It'll be able to donate that lone pair to the acceptor, and that lone pair being donated will turn into a bond as a result. All right, so that's Lewis acid versus Lewis base. Bronsted acid versus Bronsted base, very similar, but we're starting to get a little bit more specific here. All right, so Bronsted base is the currency when we're talking about Bronsted acid and base is going to be protons, H plus. Okay, this is a hydrogen atom, but it's lost its only valence electron. It's only electron, and so it has a positive charge overall. A Bronsted base is going to be something that accepts that H plus because it has the electrons to attract it, and the Bronsted acid is going to be whatever gave up the H plus. All right, so that's Bronsted. We're dealing with H plus acceptor versus source. Lastly, we have the Arrhenius definition. An Arrhenius base, we're going to be more specific. It's not just any old plain H plus acceptor, but in the Arrhenius definition, it must be a hydroxide anion, okay, OH minus. All right, OH minus, it'll use its electrons. Okay, we have 3 lone pairs on the hydroxide. All right, so it has 3 lone pairs available. It'll use one of them to form a bond with your Arrhenius acid proton. Okay, your Arrhenius acid is the proton source. See, same definition here. All right, this is your stereotypical acid-base reaction where you make a water molecule. Okay. In Chem 101, in Intro Chem, we're mostly working at this sort of level, especially when we're doing other fancy schmancy things like pH calculations and stuff like that. But you should be aware of these other definitions as well. I think it's good to learn them all because you get that common theme that regardless of what type of base or what type of acid you're talking about, this is the stuff with electrons, this is the stuff wanting electrons. And that's how you're going to be forming bonds between the base and the acid. All right. So I teach from bottom up, so you can see that we're getting more and more specific. I like to teach like a square versus rectangle versus parallelogram quadrilateral if we were to keep going. But we're getting into a more specific. That's more specific. That's less specific. Even less specific. That's an example of this. That's an example of that. But doesn't necessarily translate back the other direction. All right. So we're going to see that through examples today. I have 5 examples planned for the day. All right, and we're going to learn something else along the way, this conjugate concept. All right, we'll save that for a little bit later. All right, so we got 5 examples. In these examples, I've already written out the equations. They're already balanced, all that good stuff. We're just trying to identify what the acid is and what the base is, okay? All right, so let's go. Here we have hydrochloric acid. Well, it's in the name, right? So that's your acid. Let's see, let's get a good color here. Acid, okay. All right, this is a hydroxide source, so this is our base. If you're asked to get more specific than just saying acid versus base, then you'd want to go back to the definitions, okay? So an Arrhenius acid, I'll just say AA, is an H plus source. Hydrochloric acid, well, there's your H plus, and that's your Cl minus, but we have an H plus there. Okay, so this would be an Arrhenius acid. Okay, and if you're an Arrhenius acid, you're automatically a Bronsted acid, and you're automatically a Lewis acid. Okay, you're all of these things. So we can put check marks on all of those. Okay. All right, and then let's go to sodium hydroxide. Here we have an Na plus and an OH minus. Okay, the OH minus is what you need to be considered an Arrhenius base. Which means you're also a Bronsted base, which means you're also a Lewis base. All right. Cool. So we've identified the acid, we've identified the base. Now let's go on to this conjugate idea. All right. What it means to be a conjugate, okay. Let's put it this way. Maybe instead of a definition, we'll put it this way. If you are an acid and you react with a base, you will become the conjugate base on the other side. All right. And then if you start out as a base, you will become the conjugate acid on the other side. All right. So we just have to track the ions and then see how that plays out. All right. So if we follow like the chloride anion here, chloride starts out with H plus, but here it doesn't have H plus anymore. It has something else. It has sodium plus cation. So here it was the acid, but chloride here is now in its conjugate base form. Okay. All right. Hydroxide here started out as a base, but at the end of the reaction, it now has a H plus on it. And if you have an H plus, that means you're an acid. So this would be the conjugate acid. All right, so you just follow the anions to figure out its conjugate form. Okay, but basically any acid-base reaction, at the end of it, you're going to have a conjugate acid, conjugate base form. I think the idea is if we were to try to push this reaction in the other direction, you'd be able to know what the acid and the base is. Whether this actually happens or is possible in the other direction, that's not the subject really so much of this class. I will tell you though, with this reaction, when you have a strong acid and a strong base, this is essentially irreversible. All right. Example number 2. This one's a funny one. I wanted to show an interesting characteristic of water. Water here's a new vocabulary word, is an amphoteric substance. Okay, like amphibians, amph meaning you can go like more than one way. Okay, amphibian, like a frog, can live in water or on land. And photeric means its behavior with respect to protons. So, an amphoteric substance is something that can be an acid or a base. Okay? Something that can act as an acid or a base depending on its context. Okay? So, to show the amphoteric behavior of water, water is an amphoteric substance, I have one water molecule reacting with another water molecule. All right, so what is going on here? Maybe I should draw this on a separate sheet just to give you an idea of what's going on behind the scenes. Then we'll get back to that sheet. So here we got water. It's got two lone pairs. And let's draw another water molecule right here. All right, so we got two water molecules. All right, this reaction is not common. In fact, when we talk about pH in a future video, we'll talk about how this reaction that we're about to draw up, this happens only if you had like 10 million water molecules. It's a 1 in 10 million chance of this happening at any time in neutral water, or pure water. So it's not very common, but it can happen. So what can happen is we talked about a little bit about lone pairs being able to turn to bonds. This electron pair will interact with that hydrogen right there. And then to form this new bond, you have to break a bond, and so those electrons get thrown on that hydroxide. All right. Now, arrow pushing mechanisms is not the focus of an intro chemistry course. Normally, I'm just drawing this in case you have the interest and you want to follow along with this. Kind of get a behind the scenes sort of understanding of how we end up with the result I wrote. But we get these two ions. Here is a hydroxide. We're used to seeing hydroxides, OH minus. And this is a hydronium cation. Okay, so we have a OH minus, and then we have a H3O plus. Okay, so yeah, this happens very rarely, and usually when this happens, you know, it goes right back to being two neutral water molecules and some other two water molecules somewhere in your cup of water would end up doing this, but it's a rare event. So this water right here, it gave away the H plus, so this would mean it's the acid. It's the acid. It gave away the H plus, and this would be your base because it accepted the H plus. All right. How would you know which one is which? We'll just pick one. So this one, we'll say became that one. We'll say this one became that one. All right. So this HOH acted as our acid. Therefore, this one is our base. And now there's the conjugate acid form right here. And you would know this is the conjugate acid because it now has an extra H plus that it can give away easily. All right, and this is the base because it can accept the extra H plus. Okay. Forgot to write the word conjugate here. All right. So yeah, if you want to get into the classifications, this is Arrhenius acid. It gave away H plus, which means it's also Bronsted acid, which means it's also Lewis acid. How about this one? I am not going to call water an Arrhenius base here, but maybe we could argue that we didn't have like a hydroxide in its isolated form, even though you could try to maybe argue there's your OH, but I'm just going to say it's AB. If you disagree, feel free to let me know. Bronsted base, yes, it accepted to H+, and it is also a Lewis base. All right. Hopefully you're starting to see a pattern. We talked about how that's an example of that, that's an example of that, and then same thing with this side. These two definitions of acid-base, Bronsted acid, Bronsted base, they literally are the same thing. And then for Bronsted base, Lewis base, you can see that these two are literally the same thing. We're just looking for a lone pair source to make a bond with. All right. All right, 3 more examples, and then I think this video is done. So, all right, we got ammonia and water. Let's see. So, ammonia here, if we go to the other side, we can see that it gained a proton. That would make it a base. And then water here, we go to the other side, we see that it lost a proton, lost an H+, so that would make this our acid. Okay, NH3, this is a, no, it's not a Bronsted Arrhenius base. It doesn't have hydroxide. This is a Bronsted base because it accepted an H+. Therefore, it's also a Lewis base. How about for water? It is an Arrhenius acid because it gave away a proton. But if this ammonia was not an Arrhenius base, I'm not really thinking about this in terms of a good Arrhenius acid base example. Okay, and therefore it would be a Bronsted base, and it would be a Lewis base as well. All right, base, and therefore right here, this is its conjugate acid form. You just follow it along. And you can also think of this as an acid because it has an extra H+ now that it can give away. And then therefore this would be our conjugate base. Okay. Last 2 examples, I wanted to show some examples where there's not going to be any conjugate acids or bases because you make only one product. Okay, in that case, there's no conjugates. All right, easiest example I could think of is the formation of water. If you're not looking at any spectator ions, then without looking at spectator ions, there's only one product to look at. This is an acid. This is a base, and you just get one molecule. Okay, no conjugates there. All right, this would be Arrhenius, Bronsted, and Lewis for both of them. All right, and then this last example, I thought this would be interesting. All right, we're gonna have 2 neutral molecules. So there's no obvious acid versus base here, right? There's no like plus and minus or whatever. So right off the bat, we can tell that since there's no H+ involved, this is not going to be an Arrhenius acid. This is not going to be a Bronsted acid. And then right here, there's no OH- involved, so it's not a Arrhenius base. And it's not a Bronsted base either because it's not accepting H+. But this is going to be, oh, did I backwards them? I sure did. Yeah, this is our base. Yeah. I could edit out my mistake, but sometimes I like to show my mistakes, even though that means more writing for y'all, so that in case you came up with the same issue, you can see that I went through it too. All right, but this is our base, the ammonia, NH3. This is our base because it has electrons to donate. All right, we go back to the original definitions. Your base, that's usually going to be your thing with excess electrons. All right, it's going to be your electron donor. Okay, and then therefore this would be the opposite. Your acid, your Lewis acid, is your electron acceptor. So this is our Lewis acid, the BH3, borane. And then NH3 ammonia is our Lewis base. Okay. And these two electrons in the lone pair of ammonia, they go to this boron, which is electron deficient. Another way you can think of boron being electron deficient is it's under the octet rule. So it's hungry for 2 more electrons. So you get something called an adduct. An adduct is basically a molecule, but adduct might get a special name to it sometimes, because sometimes these bonds formed in an adduct, they're a little bit weaker sometimes compared to the normal covalent bonds you find in a molecule like water. Sometimes the adduct bond is just left like that. Other times people leave the bond looking like an arrow, kind of like here, to kind of indicate the direction of where the electrons came from. And so this would be an ammonia borane adduct. This was our base, and that was our acid. Okay, in the Lewis definition. All right, so hopefully I gave you several ways of thinking about acids and bases. For this video, I have it mostly geared towards like Chem 101, Chem 111 sort of students, and admittedly, very, very admittedly, what you all will work with most of the time is working with Arrhenius acid and base examples. In those cases, you're really looking for the H plus source versus the OH minus source. All right, hope this helps, and our next video will be pH. Thanks, take care.